So let us do the analysis of the number of probes that may be required. To access a given element in a hash table. Notation might be a little bit different. Let us say that we have a hash function. I'm using capital H here. H that uniformly distributes nodes the keys and let us say that I'm starting with slightly different notation. Earlier I talked about n. Let the table size be n, and let there be k keys already in table. Okay. Now we assume all keys are equally likely, and let us say I want to, basically the idea is to find out how many extra probes that may be required, whether it's for insertion or deletion does not matter. So, so we are trying to insert a new key into this table. Okay, let's say we are doing this. Now, the probability of hitting a free location a free location is 1 minus k by n. Okay. So on the first trial itself, I will get basically, let me call this P1, 1 minus k by n, which is equal to n minus, 1 minus k by n minus k by n. That means 1 probe. Okay. Now suppose it needs a second probe. What will P2 be? P2 is k by n. That means there was a collision, and n minus k by n minus 1. Okay, because there is a collision, and you're going to try hopefully a new location because you'll find the empty location. Similarly, P3 will be k by n into, you can work this out, k minus 1 by n minus 1, because again it collided, and n minus k by n minus 2, and so on. Similarly, we can write Pi equal to k by n into k minus 1 by n minus 1, k minus 2 by n minus 2, and we have n minus k by n minus I plus 1. Okay. The expected number of probes, number of probes becomes, what does it become? K plus 1 for the, sorry, expected number of probes for the insertion of K plus 1 element key is therefore ek plus 1 equals summation 1 to k plus 1 IPI. And this will turn out to be equal to n plus 1 by n minus k plus 1. This is the expected number of probes. This is also the okay. So this is the expected number of probes required for. So this is the expected number of probes required for inserting the k plus 1th key. And remember, whether it's insertion or search is the same. Number is same. Okay. No, under retrieve also it's going to be the same. Now what we can do is we need to compute the average number of probes needed to access a random key in the table. Okay, because we already put the elements in the table, which is the same as this. And let's call this E. And let us say that let there be n keys in the table. Then E is equal to 1 over m, k equal to 1 to n ek. And what will this be? This will be n plus, you can do a little bit of simplification and write this as k equal to 1 to n, 1 by n minus k plus 2, which is equal to n plus 1 by m into hn plus 1 minus hn minus m plus 1, where hn equals 1 plus half plus, can verify this. And this is the harmonic function. And it can be approximated by ln of n plus gamma. Gamma is Euler's constant, and if we let alpha equal to n by n plus 1, which is the loading factor, because there are n keys and n locations. We obtain E is equal to 1 over alpha ln of n plus 1 minus ln of n minus, I'm using this approximation here, plus 1 over alpha n ln of n plus 1 by n plus 1 minus n. Okay, is equal to minus 1 over alpha ln of 1 minus alpha. Okay, so one way of looking at it is, and there are some analysis that you can do, and you'll find that for I think 70% loading factor, you won't require more than log n probes on the average. But of course, there could be one element for which you might require a large number of probes. So let me stop here.